Were you the one that handed the homework in and on paper last week?
No, I did online.
Okay, okay. Someone handed it to me in person, but they didn't put their name on it, so I'm trying to figure out who it was. I'll just ask the class later. Oh, Jade, okay, okay. Okay, yeah, because there's 2 people that didn't grade, but I have 1 sheet. Okay, I'll give her credit for that. Thanks, MJ.
And for the homework, you replaced the second homework.
Yes,
I tried to do it and it was kind of.
it's definitely more difficult than the first one there. Mhm. Yeah, especially, I think especially the one with the non-standard conversions, I think people kind of struggle with that one usually, so,
No, so yes.
yeah. Mhm.
You told me to- Yeah. Yeah.
but, maybe we'll get that. Got my notes.
It's fine.
It's a year. I think it's so this is so this stuff is this stuff that I did before is right, that's why I made it so just like is that also why? I was expecting it to. Oh, you know, my phone was like so. You know, like. I'm thinking about my chill. For some reason, it's just a search. It's just. Oh,
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. All right, so week 4. So we're really in the thick of things now. Okay, so announcements. So homework 2, remember, is posted, and so remember that is due this Thursday, and so it's due at 11:59 p.m. And the topic for homework 2 are primarily cash flow conversions. Mostly the non-standard variety. So I think that that's problem 3 in the homework. And there's also a little bit of present worth analysis on there as well. Okay, so you definitely should have everything you need to do the homework. Remember, it's due this Thursday. I'm just about done grading homework 1, and so I really just have to put 3 more into the grade book. I was working on it before I came here. So I did post solutions for homework 1, and so if you look on the weekly page for week 4, which is this week, you'll see homework 1 solutions, and then basically right after the class, you should see your grade on there as well. Okay. All right, and so that's about it. So the plan for today is I have just a little bit of content from present worth analysis, mostly just one example with capitalized costs. I think we finished last Thursday talking about that, so I want to make sure I do an example so you can see how that works in action. And then we're going to move on to our next topic, which is annual cash flow analysis. Okay, and what you'll see is annual cash flow analysis is just a different flavor of present worth analysis, and so. If you kind of understand conceptually what's going on with present worth, annual cash flow will just be, just a small step forward. Okay. All right, and so, and with annual cash flow analysis, this is going to be the last topic that's going to be on the first midterm. And so I should have looked this up before I came here. So the first midterm, it's going to be not next week, but the week after that. And it's going to cover basically everything up to this the end of this week, which is annual cash flow analysis. Okay. All right, and so that's all my announcements. And so are there any questions I can answer before we get started today? Okay. All right, so let's go ahead and get started. And where we left off last time was with this idea of capitalized cost. Okay. And so the idea of capitalized costs is that, just kind of based on how interest rates work and how you can, collect money from an investment. The idea of a capitalized cost is that, you set aside a very large amount of money in the present day, and then all you do from then on, you just kind of collect on the interest rates each year or each month after that. Okay. Okay. And so even in situations when the interest rate is quite low, usually when you're talking about capitalized cost, you set aside, the money you set aside is such a large amount that even just a small percentage of that is still a significant amount of money that you can use towards other things. Okay. And so the formula for this is quite simple. So, you have a very large present sum, okay? And so this P here is a very large amount of money. Okay. And the idea with capitalized costs is that, when you set aside this very large amount of money, you put it in some kind of investment account or some kind of investment, you invest in the market, and then you don't touch it. And so it's an amount that you put in, and then you just collect on the interest after that. Okay? So do not touch. Okay. And then each year, what's going to happen is that based on the interest rate, this is the amount of money that you're going to earn just by setting aside, just passively, just by setting aside that large amount of money in the present day. Okay. 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 And so what can happen then is that because you're collecting on this interest at regular intervals, what we can do is we can say that, based on this capitalized cost that we set aside, we now have a uniform series of payments or uniform series of benefits that we receive based on that. Okay. And remember, our symbol for uniform series is A. And so what we say is A is equal to I times P. Okay. And then if we solve for P, because most of the times we're interested in P, right? And so if we solve for P, we just divide both sides by A. Okay. And so this is our formula here for capitalized costs. So usually the way this works is that, if you're interested in earning a certain amount of money each year or each month, you have that number, you set that as A, and then what you do from there is you just divide by the interest rate, and then that tells you how much money you need to set aside to generate this amount passively. Okay. Okay. And so I think last Thursday, we talked about the idea of university endowments. And so, I think, if you look at any kind of college ranking out there, a lot of colleges are ranked by the size of their endowments. And you'll hear just absolutely ludicrous numbers for these. Like Harvard has like hundreds of billions of dollars in endowments. And so that doesn't mean that Harvard has, literally $300 billion in the bank. It means they have $300 billion in investments in their endowment. And then what they do each year is that based on how those investments are doing, then they withdraw that money from that account in the form of a uniform series. Okay. But that endowment, that is basically their capitalized cost. All right, so I wanted to do an example. I think we did a fairly simple example last time, but I want to do kind of a more realistic one that shows, how a city or how a local government can set aside money for kind of a very long-term project. Okay. Okay, so let's say that the city of LA, they want to build a pipeline to transport water from a nearby reservoir. Okay. Okay. And the cost for this pipeline, because the water has to travel very long distances, because we are perpetually in drought here in Southern California, this pipeline is going to cost $8 million. Okay. All right, so this pipeline, it doesn't have any maintenance costs, but every 70 years, this pipe is going to have to be completely replaced. Okay. And just for now, we'll assume for a second that every 70 years, we're going to replace it at the same cost as what we bought it for, okay? Which is very unlikely, I know. I just got an email today that inflation over the past year was 8.3%, which is a lot. But we'll assume just for the sake of this problem that it's gonna cost $8 million again 70 years from now. Okay. Okay. And so if we assume an interest rate of 7%, what we want to do is we want to compute the capitalized costs for building and and replacing this pipeline. Okay. Okay. Because what the city wants to do is that they don't want to worry about it 70 years from now and worry about raising money, for this pipeline. They want to set aside the money now because they see that this pipeline is a very essential infrastructure, and the city's going to continue to rely on this for at least the foreseeable future. And so they want to set aside the money now, put that into the market, and then grow that over time so that when the 70 years comes up, the money will be there for them to to replace the pipeline. Okay. Okay. And so what we can do is we can draw a cash flow diagram for this, or at least an abbreviated one. Okay. Right, so I'm not going to draw 70 tick marks or 140 tick marks. Okay. But the costs that are associated with this is that every 70 years, including the initial cost, we're going to have a single cost of $8 million. Okay. And then so on and so forth for the foreseeable future. Okay. Okay. And so we want to turn this into a capitalized cost. And so, we're going to be using this formula right here. Okay. And so we're going to be using this formula to compute P. We already have I. And so I is given to us in the problem. So we know I here is going to be 7%. Okay. Right. We just have to compute the equivalent A. Okay. And so the A is something that we're going to need to, to compute this. Okay. And so the extra costs, and so, if we take the initial cost kind of out of the way, because that's something that we're going to, the city is going to raise it and then they're going to pay right away. Okay. What the city is worried about is actually going to be the future payments. Okay. And so in order to actually compute a capitalized cost from this, the first thing is to take all of the future costs and transform that into a uniform series. Okay. Okay. And because of the way that the uniform series is defined, the way a uniform series is defined is that it's defined as kind of a recurring payment all throughout, right? And so we're only going to kind of focus on just the first one here. Okay. And so we're going to focus on just the first period of 70, and then we're going to assume that we can just repeat that calculation, for everything else. Okay? And so if we just look at the first 70 years, the only future cost that we have is just a single lump sum at year 7. Okay. And so if we have a single lump sum at year 70, that counts as a future sum, or F. Okay. And so this $8 million, this is an F. Okay. Then what we need to do is we need to convert this to an A. Okay, so let's go ahead and do that. And so we have A is equal to $8 million. Okay. I'm going to use the compound interest tables for this, just because it's going to be a bit longer calculation. Right, and so since we want to convert this to an A from an F, and so our conversion factor here is going to be A over F. Okay. Our interest rate here is 7%, and then our time period is 70. Okay, and so if you look that up in the tables, this conversion factor right here is 0.00062. Okay. And so you do the arithmetic, you multiply those two numbers, and you get 4,960. Okay. And so that single payment of $8 million at year 70 is equivalent to $4,960 each year leading up to that. Okay. And so what this tells the city is that they need to raise $4,960 each year from their capitalized cost. Okay. All right. And so now that we have this A right here, we can now plug it into our capitalized cost formula. Okay, so our capitalized cost formula is P is equal to A divided by I. Okay, let's plug in the A that we solved for. So 4,960, excuse me. And then we divide that by the interest rate. The interest rate is 0.07. Okay. And then what we get from that is $71,000. Okay. And so remember, the interpretation for the $71,000 is that they're going to set that aside today. So they're just going to stuff it into a bank account, and they're just never going to touch it. Right? And so each year that $71,000 is going to generate that $4,960, okay, which they're then going to reinvest into the market, and then that's going to keep generating more and more funds. And then by the time the 70th year comes around and the pipe needs to be replaced, all the money is there, for them to replace the pipe. Okay. And so to compute all this in total, and so if we take the $71,000 and we add it to the $8 million that we needed to initially build the pipe, then the total cost for this, in the present day is going to be $8 million, $8,071,000. Okay. This right here is our initial cost. This right here is our capitalized cost. Okay. And so you add them up, and what we get is $8,071,000. Okay. And so that's an example of how, capitalized costs is used to basically provide, persistent funding for a project like this for a long time. Okay? And you'll see, and so you'll see this a lot for public works infrastructure projects where, where the public kind of depends on these kinds of, projects being there in order to have essential services. And so, it's not uncommon. Nowadays, it's a little bit more uncommon just because money is a bit tighter for for projects to be funded like this. And so a local government, state government, federal government will just set aside a bunch of money right now and then just collect on the interest to fund these projects for basic whatever. Okay. All right, any questions on this? Okay. All right, and so that's it for present worth analysis. Okay, so now we're going to move on to our next set of lecture notes, which is annual cash flow analysis. And like I mentioned at the beginning of class today, this topic right here of annual cash flow analysis will be the last topic that's going to be covered on the upcoming midterm. Okay. And so I believe this should be lecture note 03, that's posted on Canvas. Okay. Okay. So annual cash flow analysis. And so, it has kind of a very different name compared to what we've seen before, but it's actually very, very similar to present worth analysis. So if you understand present worth, you definitely understand annual cash flow analysis. Okay. And so annual cash flow analysis is just, again, another way to perform economic comparisons. Okay. And so the problems that we'll be doing are going to look very similar to our present worth problems. So oftentimes you're going to be given multiple options, 2, 3, 4 options. Okay, and the goal is to use this technique to determine which is the best alternative to go with. Okay. The only difference here is that instead of converting all of the cash flows into a present sum, in annual cash flow analysis, we're instead converting everything into a uniform series. Okay. And so instead of converting everything to P, you're going to convert everything to A. Right? But then you're still going to be doing the same thing. So after you convert everything to A, you're going to look and see which one is the highest. Right? And so either it has the highest amount of benefits or has the least amount of costs. Okay. And then that's the one that you end up going. Okay? And so, you're just converting to a different cash flow form, but in essence, it's still doing the same thing. Okay. And so, you might ask, why do we even bother with this? Why do we have, 2 different techniques to kind of do the same thing? Well, the interpretation here is a little bit different. Okay. Okay. And so when you compare it to present worth, present worth, when you compute it, is just a single lump sum of money, an equivalent lump sum of money that you would have today, right? And so it's just a single amount. Sometimes, for certain projects, it's better to interpret it instead as something of, a uniform series payment or recurring payment that's going to happen every single year. Okay? And so this is especially true for kind of the, kind of the business side. And so, for kind of the business side of engineering, a lot of times you're talking about, what are the quarterly profits, what are the yearly profits, right? And so, annual cash flow analysis will help put things in terms of that. Okay, instead of just having one lump sum today, you can kind of say, how much does this mean over each year over the course of the project? Okay. It also helps sometimes, if you're thinking about like a loan, okay? And so when you think about a loan, you think about, how much do I have to pay each time period? Okay? Because a lot of times when an engineering company has to borrow money to satisfy a project, they're not thinking about the present day sum of that loan, right? That's kind of what they've already, received. Instead, what they're looking at is, how much do we need to pay each month or each year in order to pay back this loan? And then how does that fit in with the other financial information for the company? Okay, and so, it's the same information. It's just, the way that you interpret it is just a little bit different. And then depending on who you're talking to, some might prefer one way or the other. Okay. But besides that, annual cash flow does give us some additional flexibility, or it actually gives us some advantages over present worth analysis. Okay. Okay. Right, and so the main advantage that it has is that when you're comparing options with different product lines or for different different project horizons, you don't have to do any kind of least common multiple, things like that. Okay. Okay. And so if you remember when we did present worth analysis, and we were comparing two different options, let's say one option lasts 4 years, the other option lasts 6 years, right? In order to actually make a fair comparison with present worth, we had to kind of extend the life of those projects. And so, we had to extend it for up until the least common multiple, right? And a lot of times that can be quite tedious because, you have to extend it, 3 or 4 times, and you have just a lot of conversions to do. With annual cash flow analysis, you don't have to worry about that because of the way a uniform series is designed. It's designed as a recurring payment over each period. You can compare different projects with different project lives, and you don't really have to do anything special with it. And so we'll do an example of that later today. Just so you can see, and I'll prove to you that it's not going to make a difference whether you do it for just one period or multiple periods. All right, any questions on this? Okay. All right, so let's start with some definitions. And so these definitions will kind of help us get started. All right, and so the first definition will be equivalent uniform annual cost. And so the acronym for that is EUAC. Okay. And so the EUAC is basically all of the costs associated with the project converted into a single uniform series. Okay. 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 Next, we have the equivalent uniform annual benefit. Okay. It's always a mouthful. Okay. And so that's our EUAB. Okay. And so similar to the EUAC, the EUAB is just all of the benefits for a project. So all the positive cash flows converted into a single uniform series. And finally, we have EUAW, or equivalent uniform annual worth. And so the EUAW is just all of the cash flows of the problem together, all the costs, all the benefits, all that converted to an EUAW. Okay. Okay. And so of course you can compute the EUAW from the EUAB and the EUAC, and so it's just the difference between EUAB minus EUAC. Okay. It's too many letters for these acronyms. Okay, so in present worth analysis, or excuse me, in annual cash flow analysis, what we're computing most of the time is going to be the EUAW. Okay. And so it's just like present worth, right? So if you recall from present worth analysis, all we did was we took each alternative or each project, we took all the cash flows, converted it to a present sum, add them up together, and that was our present worth. Okay. In annual cash flow analysis, we're looking for the EUAW. And so we're taking all the cash flows, converting them all instead to a uniform series, adding them up together, and that's going to be our EUAW. All right. Any questions on these before we do an example? Okay. All right. So let's redo an example from last time, except we're going to use annual cash flow analysis instead of present. Okay. All right, and so in this example, let's say that we're deciding between purchasing two different machines. Okay. We have machine A and machine B. And so machine A has an initial cost of $10,000. And the idea with buying this machine is that, it's going to automate some of the processes at the company. And so it's going to save the company some money. And so if you buy machine A, this is going to result in $3,000 cash savings each year. Okay. Machine B had an initial cost of $13,500. Okay. Initially, you're also going to have $3,000 savings for the first year. Okay. But then this is going to ramp up. And so in addition to the $3,000, you're going to have an additional gradient of $500 each year. Okay. And we can model that as an arithmetic gradient. Okay, so we have a $500 gradient. All right. So let's say that we have an interest rate, our I here is 7%. And our analysis period for both of these machines is going to be 5 years. Okay. And so what we want to do is we want to use annual cash flow analysis to determine which of these machines that is would be the best to buy. Okay. Okay. All right, so remember, for annual cash flow analysis, we're going to take all these cash flows for both of these projects and convert them to A's. Okay. Okay, so let's start with machine A first, or the first machine. Okay. And so machine A has an initial cost of $10,000. Okay, so we have a minus 10,000. That 10,000 there, because it's being incurred initially or at the beginning of the period, this counts as a P. Okay. And so we're going to need to convert this P to an A. Right. And so the conversion factor that we want is A over P. Our interest rate here is 7%. And the number of periods here is 5. Okay. And so to that, we're going to add the cost savings of $3,000. Okay. Since that $3,000 is already in uniform series format, right? It's already, it's already going to be the amount of money you save each year. We don't have to convert this one. And so there's no conversion factor needed for that 3,000 because it's already in the form that we want. All right, and so we can look these up in the table. And so this conversion factor right here in the compound interest table is 0.2439. Okay. And so we perform the arithmetic, we multiply and we add it up. We get an EUAW of $561. Okay. All right, so let's pause a second before we compute the EUAW of machine B. Okay. And so what we get is an EUAW of $561, okay? And so what this tells us is that if the company chooses to purchase machine A, accounting for the initial cost and accounting for how much money it's actually going to make or how much money it's going to save each year, it's equivalent to the company saying that, we're going to get an additional check of $561 each year over this 5-year period, because that's the equivalent annual uniform series for that machine. All right, so now let's do the same thing, but for machine B. And so we have initial cost of 13,500. And so just like we did above, we're going to convert this to a uniform series, okay? And so that's going to be A over P, 7% and 5. Okay. To this, we're going to add our $3,000 cost savings, okay? And so machine B has that as well. And again, since this is already in a uniform series format, we don't need to convert this. And so we just leave it as 3,000. And then finally, we have the gradient. And so the gradient here is 500. Oh, sorry. Okay. Okay, so we have a gradient of 500 here, but we need to convert this to an A. And so this is going to be A over G, 7% and 5. Okay. All right, so let's look these up in the tables. And so first we have A over P, 7% and 5. And so that's the same conversion factor that we had for the first machine. Okay, so that's going to be 0.2439. And if we look this one up in the table, this A over G, this one is 1.865. All right, and so if we go ahead and add these up, what we get is $640. All right, and so now that we have the EUAW for both machine A and machine B, we can make an informed decision now, right? And so based on these EUAWs, then the best machine to buy here would be B. Okay. Okay. All right. So one thing that's important for these problems, and this goes for present worth analysis too, is that it's important to kind of make this, make this statement right here of which machine is actually better. Okay. I know it's obvious, you do all that work to compute the present works, you do all the work to compute the EUAWs. In this case, it's obvious that 640 is greater than 561. Right? But remember, the point of these problems is to make a decision. Okay. And so what you're going to do often in professionally is you're going to take this analysis and you're going to forward that to whoever's doing the purchasing for you. Okay. And so whoever's doing the purchasing is not going to want to look at a bunch of numbers, even though it's just a couple of numbers that are simple. Okay? So what they're going to look at is that, or what they want is they want an email that's very simple that says that buy this thing. Okay. And so that's true for these problems too. And so for these problems, it's going to take you just a few more seconds, actually physically write out, which choice is better. Right? And so I'm going to be looking for that on the homeworks and of course on the exams as well. Okay, any questions on this? Okay. All right, let's do another example, but this time let's do an example where the product lives are different. Okay? Remember, one of the big advantages of annual cash flow is that you don't have to make any adjustments if the useful lives of the projects are different. Okay? And I'll prove it to you with this example. And so with this example, you know, we're going to be comparing two products that have different lives, right? And so, you know, the first way we're going to do it is we're just going to do it just straight up with annual cash flow, and we'll get some certain numbers. But then I'll redo the problem with the least common multiple approach, and you'll see that we actually get the exact same thing, you know, using annual cash. All right. So let's start this up. And so, you know, I think this is also a rehash of an example we did last week. And so let's say that, you know, you're working for Southern California Edison, and you're considering to purchase a new pump to kind of aid with the operations. Okay. So I'm going to summarize that in a table. So we have pump A, pump B, all right, so we have first we have initial costs, both pumps. Okay, we're going to look at the salvage value for both pumps, as well as the useful life, so how long the pump is going to last. So let's do pump A first. So pump A has an initial cost of $7,000. The salvage value is $1,200. Okay, and that's when the pump reaches its end of life. And the end of life for pump A is going to be 12 years. Okay, so pump A is going to last for that long. Okay, pump B will have an initial cost of $5,000. Okay, the salvage value for that pump is $1,000. But pump B is going to have half of the useful life, and so it's only going to last for 6 years. Okay. Let's again assume an interest rate of 7%. Okay, so we're going to use that for the calculations. And so what we want to do is we want to use annual cash flow analysis to decide which pump we want to buy. Okay. All right, so just like we did with the previous problem, we're going to compute the EUAW. Okay. All right, so let's do it for pump A first. And so for pump A, we have an initial cost of $7,000. Okay. Since that's an initial cost, we have to convert this to an A. Okay, so we have an A over P conversion factor. Our interest rate for this is going to be 7%. And since pump A has a useful life of 12 years, we're going to stretch this out for 12 years. Okay. All right. So that's the initial cost. Now we have to take the salvage value into account. And so the salvage value here is $1,200. Right, remember, salvage value is a cash flow that occurs at the end of a project's life. Okay. And so instead of being a P, this $1,200 is an F. Okay, so to convert this to a uniform series, we need an A over F conversion factor. Okay. And then we're going to do this for an interest rate of 7% and for 12 years as well. All right, so just like we did before, you know, we have these conversion factors, and so we can look these up in the table. Okay. And so first we have A over P for 7% and 12. This is 1.259. then our A over F conversion factor is 0.055. Okay, so both of those came from the compound interest table. And so we compute these, and what we get is, oops. Sorry about that. All right, and so we plug these numbers in, 7,000 times 0.1259 plus 1,200 times 0.0559. And what we get is a negative $814. Okay. And so you see, even for this one, since we're not considering any of the revenue that this pump is creating, then our EUAW here is negative. Okay. And so even with the salvage value, we still end up with a negative EUAW. Okay, so let's go ahead and do the same thing for B. And so the conversion factors for this are exactly the same. It's just the numbers are different. And so let me go ahead and fill these in. Okay. All right, so first we have the initial cost of 5,000. Okay, just like above, we have an A over P factor. Okay. The interest rate here is 7%, just like above. Okay. Right. But here, since pump B is only going to last for 6 years, right? That means for the EUAW, we only convert this up to its useful life, so for 6 years. Okay. And so we're going to do the same thing for the salvage value. So for the salvage value, just like pump A, we have the same conversion factor of A over F. The interest rate there is 7%, but instead of 12, we're going to use the useful life for this pump, which is 6 years. Okay. All right, so once again, we're going to look these up in the table. And so this A over P 7% 6 is 0.2098. And then this A over F 7% 6 is 0.1398. Okay. And so we plug all those things in and we get minus 909. Okay. All right, and so from this annual cash flow analysis, we can conclude that because pump A has a less negative, or I hate that term because it's too many negatives, but it has a higher EUAW, right? It's only minus 814 versus minus 909, then pump A is the better choice here. Okay. All right, any questions on this? All right, but you're probably thinking, but wait, that was too easy, right? And so, these pumps have different lives. Like, can we really just, skip all that work of finding the least common multiple? Well, let's see, okay? And so for this problem, I kind of picked this on purpose because the least common multiple, the LCM here is actually 12 years, okay? Right, which just so happens to be the exact life for pump A. And so pump A, if we were to do the least common multiple approach, we wouldn't do anything for pump A. Okay. But for pump B, if we wanted to extend this up to 12 years, we would have to buy a replacement at year 6. Okay. So let's go ahead and redo this analysis and let's kind of pretend that we're going to do that. And then what you'll see is that the EUAW is still going to be the same. Okay. Okay. All right, and so what we're going to do is I'm going to take pump B and I'm going to extend it up to 12 years, okay? Because that's, again, the least common multiple. And so we're going to assume that we buy a replacement in year 6 so that we take this up to 12 years. All right, so let me go ahead and draw, just because it'll be easier to visualize. Let me go ahead and draw the cash flow diagram. Okay, so here we have the 12 years. First thing we have is our initial cost. And so we buy the initial pump at time period 0 for $5,000. Okay. And then what else do we know about pump B? Pump B, we know that we salvage for $1,000 on year 6. Okay. Okay. All right, so that's our cash flow diagram for just the first pump B. Okay, so we bought pump B for $5,000. We use it for 6 years, and then at the end of 6 years, we salvage its parts. You know, we take it apart, we sell the parts on Craigslist or something. We get like $1,000 back. Okay. And so to extend this up to 12 years, you know, what we're going to need to do is at year 6, as soon as the first pump breaks down, is we're going to need to buy another pump here. Okay. And so in orange here, that's going to be indicating the second pump. Okay. And just like the first pump, you know, we're going to buy it for $5,000. But instead of purchasing it at year 0, we're purchasing it at year 6. And then 6 years later, after we purchase that in year 12, we're going to salvage it for $1,000. Okay. So this is the cash flow diagram. And so let's go ahead and convert this to a uniform series over this 12-year period. Okay. Okay. And so this is actually a good kind of an example. You know, if you're working on the second homework and you're stuck on some of the non-standard cash flow conversions, this one has a very textbook non-standard conversion here. Okay. All right, so let's start with the easy ones first, though. Let's start with the initial cost on year 0. Okay. And so the initial cost at year 0 is minus $5,000. Okay. And then we need to convert this to a uniform series. And so again, we have A over P, 7%. And we're going to use 12 in this case. Okay. So last time we used 6 because we only were examining it up to 6 years. This time we're examining it for up to 12. And so you know, we need to convert everything to a uniform series for up to 12 years. Okay. So that's that one there. I'm gonna do the one at year 6 in a second because that one's a bit more complicated. But let me start with the one at the end. This one's a little bit easier to work with. Okay. And so if we start at the one at the end, you know, this is a future sum that's occurring at the very end of the period. Okay, so this is a very standard way to express a future sum. So this is going to be a plus 1,000. Okay. We're converting from a standard F to a standard A, right? And so we have A over F, 7% and 12. Okay. Okay. And then finally, we have this, you know, we have this quantity here, right here. Okay. And so this is a single lump sum, and we can lump those together into one. And so we can say at year 6 we have a net minus $4,000 of cash flow. Okay. we have a minus $4,000 cash flow occurring at year 6, but we want to convert this to a uniform series over 12 years. Okay. And so this right here is a non-standard conversion because we're looking at an F in year 6, but we want to stretch that out to an A over 12 years. Okay, so let's go ahead and do that. Okay. So first thing I did, I just combined the two. So a minus 5,000 and a plus 1,000. And so net, we have minus 4,000. Okay. And I'm going to convert this using two different conversions. Okay. First thing I'm going to do is I'm going to take this future sum and then move it back to present day. Right, so I'm going to do a P over F conversion. And that P over F is going to be for 7% and 6. Okay. And what this is going to do, it's going to convert that F into a P. And so relative to year 0, this F here is occurring 6 years into the future. And so that means that, the conversion factor we want is P over F, 7% and 6. Okay. The 6 here being P. Okay. So now that we have, after we perform this conversion right here, we have something that's in P form. Okay. And so all we have to do from here is that now that we're in P, we can go ahead and convert this into an A. Okay. And so we're going to apply A over P, 7% and 12. Okay. This right here converts the P to an A over 12 years. Okay. All right, and so we have a bunch of conversion factors to look up in the tables. Okay. And so, but luckily, I think we did most of these up here. Okay. And so the A over P 7%, 12. We have that twice here. And so this is going to be 0.1259. Zero 0.1259. That's right. Yeah. Then we have the A over F 7%, 12. That's 0.0559. That's weird. Couldn't scroll down. Okay. And then finally, we have this P over F 7%, 6, which I actually don't have here. I don't have it in my notes, but this is one more conversion factor you can look up in the table. Okay. And so we did all this work, and then what we end up with is minus $909. All right, so let's compare that. That was a lot of extra work. And so we had to draw a cash flow diagram. We had to do a non-standard conversion. We had to buy the replacement, right? Let's compare this to the way we did earlier. We just kind of ignored all that, okay? And so if we look at what we computed before, when we ignored all that, right? We got the exact same thing, right? So we did all that extra work and we got absolutely no benefit from it. Okay? But that's a good thing, right? And so, even though we end up getting the same thing, we learned some very valuable information here. And so what that information was is that, when you're doing annual cash flow analysis, You can do it for situations when the useful lives are different, or you don't have to worry. But we can only do this under certain conditions. Okay? And so there are a couple things that lined up really nicely in that previous problem that made it so that we could actually do this. Okay? And so let me go ahead and write those down. Okay? All right, and so you can only do this when if the useful life of the or basically if there's a reasonable and least common multiple that that exists for all the alternatives. Okay? Okay. And so in the past problem, in the problem we just did, there is a reasonable one. And so, one of the project lives was 12 years, the other one was 6, right? And so all we had to do is just kind of multiply the second one by 2, and then we get, the least common multiple. Okay. And the second condition is that we assume that we can perform any kind of replacements at the exact same cost and performance. Okay. Okay. Right, and so that's what we did in the last problem. And so in the last problem, we assumed that once we reach the end of its life at 6 years, we just purchase another pump for the exact same cost and salvage value. Okay. But there's actually another situation where you can actually perform this. And so, this first condition here, this one's a little bit flexible. And so, in the previous problem, we had kind of a reasonable least common multiple between the two. Okay. But, there's another situation where we can actually do this. Okay? Another situation is when, if the equipment that we're buying or the projects that we're doing is planned for use for an indefinite amount of time. Right. Another way that we describe this is that we often say that we assume that we have a long horizon. Okay. Okay. All right. And so in these situations where the problem says that you have either a long horizon or you're using it for an indefinite amount of time, you don't have to have a reasonable least common multiple. Okay. Okay. All right, any questions on that before we do an example? Might be the last example we do today. Okay. All right, and so let's go ahead and redo the last example, but let's say that for pump B instead will have a useful life of 9 years instead of 6. Okay. Okay. All right, so pump A is still going to stay the same. We're not going to change pump A. Okay. And so if we compare these two now, so pump A here is 12 years of life, whereas pump B is 9 years. Okay. And so the least common multiple in this case is 36 years. Okay. Which still isn't awful. And so, that's, that's not too unreasonable amount of time, but it is very large. And so, 36 years, a lot can happen. Okay. And so this would be a situation where the least common multiple is not as reasonable as it was before. But, if the problem has kind of these magic words in it, so assume the pumps are planned okay. And so if the problem says that the pumps are planned for use for an indefinite amount of use, then we can ignore the the lines. Okay. All right, and so in that case, we can go ahead and recompute the EUAW for pump B. Okay. Let's assume that I here is 7%, so just as before. Okay. And so let's compute the EUAW for pump B. Okay. And so pump B had an initial cost of $5,000. And so we're converting that to an A. Right, and so the conversion factor that we need is A over P, 7% and 9. And then to that, we're going to add $1,000. Stop doing that. So this is the salvage value. Okay. The salvage value that we're now going to be salvaging at year 9. Okay. Okay. And so since this here satisfies all of our requirements, so, first of all, we're planning to use this indefinitely. And second, if we assume that, we can buy replacements for this pump whenever we need to, at the same cost and same performance, then we can just leave it like this. Okay, so we don't need to do this up to 36 years. We just look at a single life cycle for a pump, which is 9 years. Okay. And so if we go ahead and plug these in, we plug in the conversion factors, and what we get is minus $684. Okay. So obviously this is a lot better than the minus 909 that we got for the 6-year pump, because now we're paying for the same price, but the pump is lasting 3 more years. And so that's why our EUAW, even though our cost and salvage value are the same, the only thing we changed here was we extended the life. We ended up with a much better EUAW as before. Okay. Any final questions on this? All right, so that's all we got time for today, and so we'll go ahead and wrap it up here. And so on Thursday, we'll continue on with these lecture notes and hopefully finish them and finish them up. All right, so thank you everyone for coming today. I hope you guys enjoy the rest of your day. Thankfully, the weather's getting a lot cooler, so I don't have to warn you about heat stroke and stuff like that. But take care of yourself, and I'll see you guys on Thursday.
Yeah. What are you studying now? But just like that's. Yeah, at the very end. I am the
I just realized right now, I don't think I put my.
Yes,
my
yeah.
homework.
I got your name from Wednesday, so
Oh, okay.
I graded, I just haven't put it in, but I'm gonna do it right now.
Okay, thank you.
Yeah.
Sorry, I just realized right now.
Oh, no problem. Yeah. Bye. Yes, and so probably sometime next week, I'll put out a study guide to help you set. Yeah.
Oh, nice, thank you.
Mhm.
No, my friend.
Any final questions from Zoom? Or close it up? All right, see you guys Thursday.